I'm Hangqian from Digital Humanities section, and my mini project topic is social distance detection. The motivation behind the project comes from the Swiss government website. It says the best way to protect yourself and others from infection is by regularly wash your hands, keeping distance, and wearing a mask. So to monitor people in public place, is a good way to control COVID. Like we can integrate the uh, system with some surveillance devices at supermarket or train station. And if the crowds of people are at a risk level, then they can take some measures to control the spread. So the social distance detection has five functions. First is detect pedestrians in the frame. And the second is camera calibration. Third is to calculate the distance between every human. And the fourth is cover a big virus on the risk people if to alert that you are at risk. And finally, to calculate and show risk statistics. Uh, Let me introduce the Yolo. Yolo is the full name is You Look Only Once. It's a very fast real-time object detection system, and actually it's one of the fastest and most accurate object detection method, and it can run to its best when utilizing a NVIDIA GPU and CUDA. As you can see on the lower left, it's a image, and in the image, there are some object detected, and there are some bounding box around the detected object and a label. And on the lower right, the image, you can see as for the same accuracy, the Yolo V3 is much lower in terms of inference time comparing to other one-stage network. It's quite fast and accurate. Next, camera calibration. Let me use the diagram of auto parking system. As we can see on the left is there is a perspective view image, and in fact the camera is on the back of the car, and when parking, actually this two lines should be parallel with each other, but actually in the perspective view image, these two lines are not parallel. So we need to transfer the perspective view image to the bird view image, which is look from the top to the bottom. And so we need to calculate a transformation matrix to do this transformation. Like we can use 4 points in this perspective and 4 points in this bird view image, and to calculate the transformation matrix, and next to apply this matrix to calculate the corresponding points in the bird view image. Luckily, OpenCV can provide a powerful function to do the camera calibration, so I do not need to do the math by myself. So, but I need to do some pre-work before camera calibrations. First, I need to mark 7 points before I shooting. The first 3 points, A, B, and B, C, should be perpendicular with each other, and the length of A, B, and B, C should both be 1.8 meters. And as for the other 4 points, D, E, F, G should form a rectangle. And so I can use these 4 points to convert, and this 4 points to get a transformation matrix, and use these 3 points to transform these 3 points to the image, to the bird view image. And as just marked, the length to be 1.8 meters, so we can calculate how much how many meter one pixel correspond in this image, so we can measure the distance between people. Another thing is cover the risk people with virus, but unfortunately there's no function to cover image with transparent channel to another image in OpenCV, so I need to do it by myself. First, I need to read a virus image and then split it into 4 channels with its RGB and alpha, and then convert the alpha channel to a mask. And I can get this, and then multiply the mask with RGB channel of the virus image, and I can get this. And next, I need to crop the background and let it be the same size of the virus image. This is the people at risk. And the next, I need to multiply the converted alpha mask with cropped background. Get this, and next I need to plus this two and get a result and put it back to the background image. Finally, I get this. Here are some parameters and hardware environment of the system. I do it using the Mac OS, and memory is 16G, and detection model is Yolo v3. And as for parameter, the confidence threshold and the non-maximal suppression is both 0.5, and output video is distance video and bird view video. As for risk level, if the the distance is higher than 1.8 meter, then it's safe and the color is green. If it's not over than 1.5 meter, then it's high risk. In the middle, it's low risk and it's yellow. Here is a video. First, I need to mark 7 points, as you can see, and run the algorithm. If the people is far away, then it's green, but if they go closer, it become yellow, and if it's much closer, then it's become red, and there's a virus to alert that you are too close with each other. If they run away, then it become a green again. You can see there's some grid in front. It's to influence the result. Okay, next. After the detection, I can get a risk level statistics. I will sum all the high risk people number across all the frames over the people number in our frames, so I can get a high risk level. And using this, just now the risk level is 33%. And using this risk level, some government officer or shop owner can take measures to control the COVID-19. There are some limitations of this algorithm. The surface has too flat. As you can see, the far person is also detected, but actually this two level is not the same level. In this level, it's much lower than this level. But as for the calculation of the distance, because we use the bottom of the bounding box, and if we calculate the distance, it is not accurate. Also, if there are some like there's a stone in front of the people, so the bounding box become shorter than it should be. So so when calculating the distance between those two people, it's not so accurate. Actually, these two people should be lower than 1.5 meters, but when calculating it's marked green, which is not correct. Another limitation is when it comes to the crowds of people. If there are crowds of people, the detection is not very good. As you can see, many people are not correctly detected. And as for some people who stand really far away, it's not accurately detected, which are two limitations of this algorithm. And here are some reference. And thank you for your listening, and welcome for questions.